All right. It's a MOS transistor only we are going to discuss, but we'll go as per the syllabus. Okay. So the syllabus, there is a normally you have one question coming from the history part of that, right? So brief history is absolutely needed. I'll go very quickly about it. Okay, so when it comes to the IC technology, right, this we need the history of IC technology, right? How it started and what are the various levels of integration that existed, right, in the past. So this is the history part of it. Okay, so there were multiple levels of integration, right? Big using integration, they could put many more transistors on a single chip. Okay, so the first integration was called as a small scale integration. Okay, this is SSI. Okay, so this is SSI around uh, 1 second, let me just check the year. Maybe this was in 1980s. Okay, then SSI actually included just 10 gates. Okay, then the second level came, this is MSI. Okay, so MSI stands for the medium scale. No specific date. All right. So just an approximate year. See, because there were few companies working on them, so they will not disclose at what date they did what. Okay, they just, you will get only approximate, right? What you call uh, year, right? So this is around 1990s. Okay, medium scale where the integration was for approximate 1000 gates. The LSI, this corresponds to large scale. Absolutely fine, no problem. Okay, right. Let me know if you need any break in the middle, right? Okay. So LSI, this is the large scale integration. This was 10 year after that, that is 2000 approximately. So this included around 10,000 or right. Sorry. Yeah. VLSI is very a recent one. So this was around 1 lakh gates, right? And then the VLSI, very large scale integration. This was more than 10 lakh. Okay, this is more than 10 lakh gates. Okay, so in the past 20 years, this has been the very important field of research because, right, the number of gates are increasing drastically. Okay, so because of that, this is the uh, this is how it evolved. Okay, the different levels of integration. And the second concept in this is the IC technology development, right? How the ICs are built up. I know that in my IC, I'm increasing the number of gates in a given area. Okay, this is what is the levels. But the IC technology is not just increasing the number of gates, but also reducing the power supply. Okay, so that curve is also equally important. So let me draw a curve here. This is also a part of history. Okay, if something is asked about history, you can tell everything about this depending on the number of marks allocated to the question. All right. So the second part of the history comes in terms of the power supply voltage. Okay, so this is the FET. This is power supply versus year, right? So the oldest one, maybe you can take around 1990. Then this is, I can say, 2000, 2000 and say 2010 maybe. Okay, this is 2010, 2020 and so on. So now you see that the latest value also I'm going to use. So originally this was starting with very olden days, it was 5 volts. Okay, then it came to around 3 volts. Okay, then it is, as the year is progressing, you have 1.5 volts, and very recently we are touching 1 volt. In the sense, just 1 volt is enough to turn on a FET. Okay, so this was, yeah, so you see that as the power required to turn on a transistor is reducing, the transistor is dissipating lesser amount of heat. That's why it is becoming more and more efficient. All right, perfect. So around, you see that this is how the curve is. It will go like this. Okay, so like this. So now you see that actually we are very close to 1 volts now. Okay, so supply voltage keeps on reducing as you, right, as you move right towards right on the year axis. So move right. So you can see that the number of sorry, the voltage required to turn on a transistor or the power supply keeps on reducing. Okay, at the same time, on the same graph, I'll try to plot another graph, right? So this is the number of transistors in a given chip, right? So around 1990, right, the total number of transistors, right, were around this value. Now it is, you see the increase is very drastic. So it's like this. So we can say that if this is around 12 million, and now we are touching almost 750 millions. Okay, so this is how it is increasing, right, on the same area. If it's like, if you take a 1 cross 1, this much area, earlier you had only 12 million, now in that same area you have 750 million. So it's a drastic increase in the number of transistor in a given this thing. Okay, so design also, there are softwares to design and placement of the transistors where you want to put the yes. So the complete circuit, starting from circuit design till the manufacturing, right? There are automatic process. Okay, right. Only the manual design part is there, right? Some part of it will be manual, but rest everything will be automatic. Okay. Plus, there is another type of what you call the evolution, right? That is in terms of the channel length, right? Channel length in the sense the gap between the drain and source, drain and the source terminal. Recall the diagram we wrote yesterday. So one was n plus, which we call as S source. uh, Yeah, approximately you can think like that, but actually the gate occupies some regions of the drain and source external. Okay, so because of which we restrict this to the word as channel length. Okay, this is also called as a process. The terminology is process. For example, this is in 1990s, right? The process was called 250 nanometers. In the sense that length was 250 nanometers technology. We say that now also. You say, if you try to purchase a, say, processor, right? I want to buy a new processor. Let's assume maybe i3, i5, i7, or so there will be a name mentioned over there saying that what technology is it, right? Or what process it is. It will be mentioned like, say, 70 nanometers. Now it is actually coming to the single digit. Now even the graphics cards or something, you can see it's coming in 6 nanometers, 7 nanometers. You see the difference, right? Earlier it was 250, now it has reduced less than 10. Okay, so 1990s, around 2000, this was reduced to 150. Okay, then 2005, this was 100. Okay, 2010, approximately 60. So 2015, it was 30 nanometers, and now in 2020 you are closing to 10 nanometers. Now it is much lesser than that. You can see the processors coming, even the mobile processors. You can see the Qualcomm or the Snapdragon processors coming. They are less than 10 nanometers now. Okay, the 5G processors which are going to come in future will be definitely less than 6 nanometers. 5 to 6 nanometer you can definitely see in soon future. Okay, so now all this evolution is actually summarized in one single law, right? That was also, it's an older law, but it's still true. It holds good. It's called as Moore's law. Okay, Moor, Moore's law. Okay, actually this law was, the person is from Intel. He gave an idea about the number of transistors, right, that can be put up inside a chip as the time progresses. Okay, so he gives a very clear idea, and that is still holding good. He told this in 1965. Okay, so that time he told that uh, the silicon technology, the silicon technology uh, doubles in terms of the number of transistors per chip every 18 months. This is what he stated, right? In the sense, at that time, maybe they were able to put 10 transistors in one chip. Okay, after 18 months, it became 20. Definitely, it will come. It will come to a limit, right? But it's still it's getting satisfied. Okay, every 18 months approximately. Okay, every 18 months, the number of transistors in a chip are getting double. So that's what your channel width is reducing by that amount. So you have your channel is reducing. You can see the same similar things happening over there, right? So as the channel width is reducing, right, you can see more and more transistors coming in place. Okay. All right. So this whole thing is related to the history of the MOS transistors. Okay. Anything related to this might come, and you may have to rearrange the or rearrange these concepts as per the question to answer the to give a answer. Okay. All right. Now we'll start with the actual concept of the MOS, metal oxide semiconductor transistors. All right. Now this is actually a layer by layer process of building the transistor, right? So you can see that the name says metal is there, there is an oxide is there, layer is there, and a semiconductor layer is there. So this is layered architecture, layered architecture to build the transistors. Okay, now you put a layer, put another layer, and the third layer will sandwich the second layer between first and third. Okay, so these structures are manufactured by using a series of chemical processes, right? There will be oxidation. You are going to implant the dopants. You deposit different types of contacts and so on. So that's why it is called as a layered architecture. Okay, now the CMOS technology can develop two types of transistors, correct? So this is actually complementary MOS. So you know the word complementary, correct? One side you develop N type transistors, at the same time on the other half it will develop the P type transistors, correct? So like that, if you develop the circuit, they are called as CMOS. This is a variety of MOS. It's called as complementary MOS, metal oxide semiconductor. So what are the two varieties are available in this? First one is called as N-type. Okay, N-type MOS, or you call it as NMOS. There is another called as P-type MOS. See, CMOS is complementary. What are complementary? One is N and one is P. So they are complementary. Okay. That's why the technology using which you develop half of the circuit with PMOS, the carriers, charge carriers are complementary, right? One will be using P, that is holes, and the other type will be N, electrons. Okay, so this is PMOS. Okay, now the whole transistor operation is controlled by what? By electric fields. Okay, electric fields are applied in such a way that, right, the device is controlled using the voltages, right? So now we are discussing only about FETs because BJTs are old, right? The applications are widely built with variety of features, right, using FETs. All right. Now, how do you control this? The operation of a transistor, okay, or I can write the transistor operation, correct, is controlled by what? Controlled by gate voltage actually, but that voltage builds an electric field inside, right? That electric field is the one which attracts the electrons present in that region. Okay, so I'll write the word electric field. Electric field, okay, that electric field is actually present in the gate region. Okay, right now we will not talk about that because we have not defined the different terminals yet. Okay, so I am not talking about which region it is. All right, so electric field, so that we can call it as, so that we can term them as MOS. MOS is understood so far. MOS, metal oxide semiconductor. Now I give the actual word, that is field. You see the word field, that's because electric field, field effect transistor. So the term is MOS, field effect transistor, or this is MOSFET. That's why the term MOSFET comes into picture. All right. So now we'll go for the general diagram of PMOS and NMOS, because we defined already there are two types of MOSFETs. Okay. So let's go to the simple diagram. We'll look into this. Okay. So first one, I'll draw both of them together so that we can give the names equally later. All right. This is the first one and this is the second one. Okay, on the top I'm going to draw the NMOS. So for NMOS I require two regions, one this and another one this. Okay, same thing. Okay, or I'll do one more thing, right? I don't have to draw two separately. First let me simply draw one properly and I'll copy this to the other place. Okay, that's easier. All right, so then I actually have another region. See, this is what I told, it actually overlaps with the other two. This is an insulator layer, and upon this I am building the gate layer. Okay, and let's define the terminals. So here we have the first one coming. This actually enters inside the this thing, and then we have another coming up over here, and the third one is here. Okay, right. So I'm trying to draw a NMOS here right now. Okay, so same thing I will copy so that I can even draw a PMOS later. Okay. Okay, now, so this is the terminal called source. I'll write S, this is G, this is D. Right, now the gate layer is denoted like this, and since this is a N MOSFET, I need N plus and N plus. I'll tell you the meaning of plus soon. Okay, and the substrate is P. In a sense, I collect a P layer and I build N layers inside that. Okay, they are called wells. Okay, now the gate layer is basically, you can see that there are two different layers in the gate. The top layer is called as polysilicon. Okay, and this layer is the SiO2, silicon dioxide. That's an insulator. Okay, silicon dioxide acts like an insulator. It will not allow the current to flow when you apply a gate voltage, because I don't want current to flow there, right, to create a channel. I just want electric field. Okay, so silicon dioxide only, it itself has been used. Why not other insulators? Means silicon dioxide actually concentrates the electric field to this region, right? Electric field should not get dispersed, right? It should be concentrated so that more electrons will come and occupy the required layer. Okay, so this is the top diagram is for NMOS, N type MOSFET. This is because, why it is called N, the channel is of N type. Okay. Similarly, and yes, drain to source, there should be current. Okay. Very similar to that. Now we write the second diagram, which is the correct. Correct. So this is P. This is N. This is P plus. This is P plus. Okay. There is a source, drain. My mistake. Source, gate, and drain. Okay, so this is the gate, this is the drain, and once again we have the polysilicon over here and the SiO2 over here. Okay, so short form for polysilicon, normally textbooks will simply use the word poly. It's understood that it's polysilicon, and this is SiO2. Now, I will tell you the significance of the plus written over there. Okay, now let us say that there is silicon, right? Silicon is pure silicon. It's a intrinsic semiconductor. If you remember the types of semiconductor, right? One is pure. Okay, I'll write the semiconductors, right? If you remember, we have two types. One is called as the pure semiconductor, pure form, which is available in nature. This is called, as the technical term is, intrinsic. Okay, intrinsic semiconductor. The second one, semiconductors, yeah, the gate material, I have to use a semiconductor. No, are you aware of the three types of materials in terms of conductivity? No? Okay. What I do, I'll go to the basics. All right. So let me come to this point later. All right. So let's look at, so if you understand that concept, uh, the technical aspects of what you call these conductivity and the valence electrons, all those things will become very easy for you to understand. Okay. Let's spend some time for that topic. Then we'll come back. Okay. So you see, there are three types of material, right? Again, we are strictly talking about how good they are in terms of the conductivity. Okay, so the first one is, I call it as insulator, correct? If you remember, insulator, it will never conduct, right? Yeah, again, we are talking about the conductivity in terms of electricity, okay? Whether it will conduct electricity or not. Okay, so maybe plastic, right? It will never conduct. Okay, so why it will never conduct, I'll come to that point slightly later. First, let's discuss about the types, and the second one is a proper conductor, right? So this means it will conduct, right, easily, right? Conducts easily. Now, let's look at these two first, then we'll come to the third one, that is semiconductor. Okay, so let me try to differentiate the conductor and semiconductor. Sorry, so conductor and insulator like this. Okay, on this side, I'm trying to look at the internal energy diagram of a conductor and a non-conductor. Okay, now let us consider this is the surface of the nucleus of a material which is non-conductor, okay, or insulator, right? This is a bad conductor, non-conductor, anything you can call, right? It is not conducting, I know that, right? So which means, let's consider this is the surface of the nucleus of that atom. Okay, now we know that the electrons are revolving around the nucleus in several paths, correct? Right. Now, if you remember, what is the outermost electron layer is called? No, shell is like a group of the paths, right? Outermost, have you heard the term valency, right? Right, this is called as the outermost, right? What you call outermost path in which electrons can revolve around the nucleus is called as valence shell, correct? So shell is actually a group of paths. Fine. Now let me say that in a non-conductor, right? Maybe any number of electrons might be present there. The outermost, right, shell can have some number of electrons. Fine. But in order to conduct, right, conduction means what? Electron will come out of that particular what you call nucleus, it will lose all the effects of the nucleus and it will jump from one nucleus to other nucleus. Okay, or right, it will break the bond and come out. It comes out. Okay, now in order to do that, right, we need a specific amount of energy. Okay, so just recall, as a electron comes closer to the nucleus, this is the nucleus. Okay, or this is the nucleus. So we have energies like E1, E2, etc. This is EV for valence shell, right? This is how it is arranged. You know that as you move as you move away from the nucleus, energy keeps on increasing. Okay, so it means valence shell has highest energy. Okay, those electrons have most amount of energy, maximum energy. Okay, but there is another point. In order to take part in the conduction, you require a minimum energy, right? That is called as EC, called conduction energy. Right. Now these in a non-conductor, the though you have many number of electrons, none of the electrons have the energy required to take part in conduction. So I call this is conduction band. Okay. Okay, this is actually very far, right? Normally what happens, so you heat that material, or you apply voltage, or you increase the temperature. Doing all those things, you see that these electrons will jump to a higher cells. Okay, but in a non-conductor, whatever is the amount of energy you supply to the material, the electrons will jump, but electrons will never reach this level. This is very far. There is a huge gap. Okay, so this gap is huge in a non-conductor. Which gap is huge? The gap between valence shell and the conduction shell. Valence band also we can say. This is a huge gap. How much ever energy you supply, the electrons will not be able to jump from valence to conduction. Those electrons which are in the conduction band, in the sense those electrons which have energy more than the minimum requirement, they can take part in conduction. In the sense, if at all you have some electrons in the conduction band, that material will conduct. Okay, right? So here you have a very huge gap. That's the first point to remember when it is a non-conductor. Now let's look at the conductor part. So conductors are like, we say, whenever I say a metal, it is a very good conductor. Why? Now I'll tell you the reason. Let us say, right, there also you have a nucleus, right? And electrons are revolving around in several paths, correct? Now you see, right, what happens here is like this. See, this is the minimum requirement to take part in conduction. I'll say this is EC. Conduction band is here. Okay. But your valence shell is here. This is EV. Are you understanding the difference? Now you see, valence means still here the orbits are completely filled. Right? Above the conduction band, you have many electrons. See, these electrons are already in the conduction band. Whatever is in this band, right? They can directly take part in conduction. You have, right, EC and EV overlapping, correct? Because you see here EC was above, EV was below. Now you see EV is above, EC is below. In the sense, so much of gap is completely filled with electrons, and those electrons have more energy than the required energy to take part in conduction. Right. So which means now this is the obvious reason why even if you give a very little voltage to a conductor, right, there is electricity flowing. Right. So you take say 1 meter wire, give just zero point 0.1 volts. 0.1 volts is actually it's a negligible amount. But if you keep an ammeter, it will show a reading saying that yes, current is flowing. This is the reason. Are you okay? Conductor has many electrons. So these electrons which actually lie above the EC level, they are called as free electrons. They can take part in the conduction, right? They exist in a conductor abundantly with a very huge number. Okay, they do not exist, right? Even after applying a external voltage, external power supply, they will never exist in a non-conductor. They will exist a lot, right, in conductor. Now the term should be, right, easy for you to understand. The third term, which is semiconductor. Okay, now you tell me, what is a semiconductor? What do you expect? If I try to draw a diagram, this is the nucleus part. I have the energy levels, right, of various electrons, right? And what should be the EV and EC, right? It's a semiconductor. It's not a good conductor. It's not conductor. At the same time, it is not a non-conductor. Under some condition, it will conduct. Okay. So the basic difference here is, let us say this is the EV, valence. Very close to that, you have EC. So you see, this EC was somewhere here. This was very far in case of a non-conductor. So the jumping of electron from this to this was very difficult. So even if after applying a huge amount of energy, this was not possible. That was an impossible jump. But you see, they are very close here. You apply sufficient amount of energy so that uh, an electron in the valence band or valence shell can jump into the conduction band. So as soon as it acquires the required amount of energy, it becomes a free electron, correct? So now the important thing is that this gap, what you see here, is a small gap. So by default, it is not a conductor. Okay, but if you apply little bit of energy, there is a calculated amount of energy if you apply in terms of voltage, temperature, light, or different ways. Okay, the electrons in the valence shell will come to the conduction band, so that you can the material can conduct. Okay, so three types of materials. I think this is fine for you now. Okay, do you have any doubt? Okay, let me know if you have any doubt. Yeah, I'm coming to that point now. Okay, immediately. So there is actually, if you are actually doping with N type, right, it means you are filling with more electrons. In the sense, the EC comes closer. At the same time, if you are doping with P type material, right, you are trying to increase the gap. Okay, it depends on what type of material you are expecting, right, what type of conducting characteristics you are expecting. Okay, so anyway, I have not used the doping yet. Okay, I'll come to that now. So if what I explained so far is fine, please let me know. I can go ahead. It's fine, right? Okay, now I'll go to the types. So let's look at the types of this. So first type of the semiconductor is actually the pure form, pure silicon, in the sense you have uh, the sand available in nature abundantly. That is actually silicon dioxide, right? So right, we take the silicon, pure form silicon, by processing the sand. Okay, so that is technically called as intrinsic semiconductor is a pure semiconductor. Okay, at the same time, we have a different types of semiconductor that is actually impure. So impure in the sense, it's not like when I extract, it comes with a mixture. It's not a mixture of them. You purposefully put some impurities to the pure semiconductor to convert this into extrinsic. Okay, now my question is, what is the requirement? When you say that you have a pure material, why do you want to make impure? By doing some unwanted, or sorry, by mixing some impurities, why do you want to get a impure one from the pure one? Yes. So in order to improve your correct, correct, correct. So it is something like the right. If you put a specific impurity, right, you can actually control the number of free electrons or the number of holes in that material. You can control, right? So in the impure, in the extrinsic, right, if you put the pentavalent. What is valent? Valent in the sense valency. Penta is 5. If the valency of the impurity is 5, this gives you N type material. So pure silicon becomes N type silicon if you add a pentavalent impurity. In the sense, penta has more N type, N, more electrons. Okay. Whereas there is another option called trivalent. Correct. So when you add a trivalent impurity, this becomes, you are adding more holes in this case, so this becomes p type. You are creating holes inside the material. Okay, so like this you can generate the p and n. Okay, right. When you add normal amount of these impurities, we call that as n, or simply p. If you call n or p, this is normal doping, right? Okay, but when you see we wrote n plus or p plus, right? This is because of extreme doping, right? You put much more impurities, right, than the normal. Okay, so that's what is called as extreme doping. When you extremely dope the material with pentavalent, it becomes N plus. When you extremely dope the silicon with trivalent, right, it becomes P plus. So that's what you can see now, what we wrote when in the diagrams like N plus and P plus. It says, see, you see the difference now. See, this region is normally doped P, okay, but these two are N plus, indicating that those regions are extremely doped. Are you okay? It's fine now, right? So same thing is true here. It is N here, P plus over there. Are you okay? So that itself is a idea about what is the, how much doping has been used. Is it normal or is it extreme? We can identify by just looking at the diagram itself. That's why we use that. Only two types. One is impure, one is pure. In pure, we don't have any differentiation. That's only one. Okay. In case of impure, that is also called as extrinsic, you have two options. You can mix pentavalent to get a N-type impure silicon, or P-type by adding a trivalent. Okay. Inside the intrinsic, you have two types. That's all. There is no other type of semiconductor. All right. So from the above diagrams, we understand that the MOSFETs have three different uh, what you call terminals: source, gate, and the drain. Okay. So it says the drain in the sense. See, what do you mean by drainage? The word is very similar. We can remember the work done by each of the terminal by using their uh, similar words. So drain, because it is actually doing a job of a drainage. When we say drainage, it is right, it is something which is there extra you want to take out, correct? That's what is drainage. So what is being drained out in this case? When I say in a MOSFET there is a drain, it's actually taking out unwanted electrons from the device. Okay, what do you mean by source? Source in the sense it is a supply, it's going to supply electrons to the device. That's why it is source. You are sourcing something. Source of electrons, it's a drain out part of electrons, it's a drain, and gate is the one which controls the flow of electrons. Correct? You open the gate means more space, more electrons can flow. You close the gate means there is no space for, so that's why the name itself is gate. You're okay? Anyway, we are going to see this in detail later. Yeah, please tell me. It's understood, right? You understood that, right? Okay, now, normally, right, the terminals are biased in such a way that the required amount of, right, conduction takes place. Okay, so before that, I will define the biasing once. So, if you remember, can you tell me what is biasing? What do you mean by biasing? Biasing is actually, you can relate this, the word biasing, to different types of biases you apply to maybe BJT, maybe diode, right? In case of diode, you might have heard biasing, right? Forward reverse bias, right? So biasing basically refers to, right? You are going to applying suitable voltages to the terminals of a semiconductor device so that we can, we have two options, right? By applying biasing, you can either turn on the device or turn off the device. Okay, we can turn on or turn off the device. So this is what is called as biasing. Biasing in the sense, either you are applying suitable amount of voltages to the terminals of that device so that you can either turn on or turn off. Now you relate this to the forward biasing of a diode, correct? Why you apply forward bias? To turn on the diode, correct? Why you apply reverse bias? To turn off the diode, correct? So same thing will hold good for the BJTs, right? There also we apply specific amount of voltage between base emitter terminal and collector emitter terminal so that your device works in a specific mode, right? Either you turn on or turn off. Okay, fine. So this word is biasing now. Normally, right? How do you bias the MOSFET? Right? Is like this. Normally, if you are considering a N-type MOSFET, right, you are going to apply, right, the gate voltage. First you will apply a gate voltage, okay, and that gate voltage will decide whether there is a conduction or, right. Now using this biasing we can actually make the transistors to turn on or turn off. Okay, so before that let me give the notations of NMOS and PMOS. Okay, so this is the notation whenever we draw circuit. So we don't use the whole diagram which we wrote earlier. So let's write a NMOS and a PMOS. So NMOS is represented like this. Okay, so this is the representation like this. So this is the drain, gate, source. Okay, at the same time, the PMOS is represented in the very similar fashion, but the opposite polarity is denoted by a circle here. Okay, this is a PMOS. Once again, drain, gate, and source. Okay, so if you see a bubble over this region, then that will be the PMOS, right? You see that it is not present here. This is a NMOS. Okay, right. Let's move on further. The next topic is the MOS transistors as switches, because this is a very important application, because you see in a IC circuit, right, I cannot put external switches, right, because the whole circuit contains lakhs of transistors, and to control any one part of the circuit I might require switch, and external switch will be much bigger than the size of your whole circuit, correct? So it's not suggested to put external switches, and the connections will become very difficult. All right, so under such condition, you can see that what we do, we use MOS transistors itself as a switch. Okay, so how can you make a transistor to work like switch? I know something from my basics. What is that? The gate of a MOS device controls the current between the drain and the source, correct? We know this. So let's write that. So the gate of a MOSFET, gate of a MOSFET controls the of current flow of current between source and drain. This means the gate is the control input, right? We already know that. So if you want to use the MOS transistor, right, you can use the gate voltage to decide whether you are going to turn on or turn off. So turn on means there is a conduction, the switch is closed. It's like turning on the switch. I have a switch for my fan. When I turn it on, fan runs. When I turn it off, fan will not run. Similarly, you can see that when gate voltage is given, there is conduction. When gate voltage is not given, conduction is not there. So it means it is a switch only, correct? Right? Right. Now, the gate terminal acts like a control input, right? As it affects the electrical current flowing between the drain and source. So I can say that this implies the gate acts like the control input. Okay, it acts like a control input now. Right, now we need to decide what happens in a NMOS and what happens in a PMOS. So how the NMOS and PMOS transistors can be used as switches is our uh, point of discussion now. All right, so let's write in NMOS. Let's see what's going to happen in a NMOS. Right, now in a NMOS, right, recall the diagram we had drawn yesterday. All right, so when the gate voltage is not there, correct, so you can say that there is no connection between the drain and the source. Okay, if no gate voltage is applied, This implies there is no channel, correct? This implies no connection between the D and S. It means drain and source of MOSFET, correct? So when there is no connection, it means even if you apply a voltage, there is no conduction. So this means the switch is off. You switched off the device, right? By not applying a gate voltage or by removing the voltage, you have turned the device off. So how do you show that device is off? You can draw a simple circuit connection like this. Let us say this is the source and this is the drain, and you have open circuited that. This is the switch is in the off position, right? You see, there is, this means the voltage applied to gate is 0. Are you okay? This is when no gate voltage is applied. Okay, let's move further. So if gate voltage is increased, right? As and when you increase the gate voltage, what happens, right? Electric field is applied, electric field appears between the drain and the source regions of the transistor, correct? Means what? Just recall what we discussed yesterday in the basics, right? As soon as the as soon as the electric field appears between the drain and source, right? Electrons get attracted by which region? By gate, correct? Gate attracts electrons and they form a channel, correct, between the D and S, which means now when you have the channel between the drain and source, right, it can conduct, correct, right? So you see that this implies the transistor is on, right? MOSFET is turned on. Are you okay? So you can just give a notation now. So you can show that there is a connection between this. It was open earlier. So source, drain, and you have the connection between the drain and source. You can say that this is turned on. Yeah. So this is how you the N MOSFET can be used as a switch. Okay, apply the gate voltage, device is on. Remove the gate voltage or reduce the gate voltage, the device turns off. Okay, very simple idea. Okay, so in tomorrow's class we are going to look at the PMOS and how the PMOS can be used as a switch first. Okay, we'll see that first, then we'll proceed further to the theory behind the complete MOS transistor. That's what is going to come up in tomorrow's class.